Hey, hello, we are Team 1, and we'll be presenting our progress on what we have done so far for our project, Transpose, a project to track human motions with only limited amount of IMU sensors. Hi, I'm Jonghi Jun, and let me introduce you to our presentation. First, we'll talk about our application process, then its offline evaluation, followed by a live demo, and lastly, some improvements that we have made so far over the original paper. First, let's talk about the replica. When we first looked at the GitHub repo that the authors gave, we found out that the training code and the dataset wasn't provided. Thus, we first have recreated the training code, and we referenced the loss functions from the paper and was able to finish up the training code. Also, we built the dataset with the SMPL body model and the AMAS motion capture dataset. We have combined those two and created a moving human. And from the human, we've selected the 6 points from the paper and was able to get the artificial IMU data needed for training. However, we have faced a problem while training with our code and dataset. It was that the code was too complicated and took so much time. It took like days to only train a small amount of epochs. So we've searched for some candidate problems, and we came up with two. First, we found out that the trans B2 loss was very repetitive and overly complicated. And also, we found out that the process of converting a rotation matrix to a 6D vector was so time costly. So we have changed them as so. We decided to use MSE loss and just use the rotation matrix itself rather than changing it to 6D. With these changes, we made some modifications to the original training code and newly trained the model. And after training, we have conducted some offline evaluations to test our replica's performance. This is the process we have went through for evaluating. We brought a data set called DIP-IMU, which is a data set that contains real IMU measurements, along with the true joint and vertex values of the human. We have inputted the real IMU measurements to our trained model and compared the output results with the ones provided from the dataset. And here's the results. The pre-trained model was, as expected, accurate. However, it required too much resources. And for our original training code, it showed bad performance on jitter error, maybe due to the inefficiency and mismatch of resource requirements with the actual resource amount we could use. And finally, for our newly constructed training code, we were able to find a sweet spot for performance versus resources. And here's the offline demo videos for our replicas. And as shown in the first one, which is the pre-trained one, it looks really smooth and accurate. However, if we look at the middle one, we can see that some jittering is happening, and also the right foot is fixed at a single point. And lastly, if we look at our final replica, we found out that it gave the sweet spot of the aforementioned two.
Hi, I'm Nuno, and I will talk about live demo progress. The strength of this paper is that it can reconstruct human motion in real time. There was also live demo Python code. Of course, we already checked angular error or position error, and also offline demo that compare model performance, but it is hard to compare how natural motion is or how well this model reconstruct human motion in live. So live demo is also important. And we tried out a live demo using our own IMU sensor, the XNStat. The paper used IMU sensor from the same company with XNStat but of different type, and we decided to use XNStat since they are smaller and newer. One thing that is confusing about the paper was, we tried to measure the IMU sensor value of the left forearm following paper. But if we look at the figure given in the paper, we can see that the IMU sensor was all on the wrist. The reason for this is that the joint of the wrist, we think, and the wrist used to reconstruction human motion was different. Therefore, it is correct to wear the sensor on your wrist that we usually think. And also, we use Unity for reconstruction and live demo. We prepare Unity code that can use human reconstruction model, SMPL, and also can get model output in line. So this is our whole real-time live demo system structure. First, we attach IMU sensor and run code for receiving IMU sensor value. IMU sensors are sending data with Bluetooth, and our receiving codes are running with async IO start server. Then we pass these IMU values to model code with socket connection. Then after inference, output value that means for human reconstruction are passed to Unity code also using socket connection. But we are struggling with some trouble. Following manual of X and start, it is said that we can connect up to 7 IMU sensors when using Windows OS. However, in practice, it is difficult to connect all 6 IMU sensors at the same time. In particular, if we connect 6 units, the hertz becomes low. Model needs to get 60 Hz input, and also when we try to connect only one sensor, it is possible to get and send data in 60 Hz, but with 6 sensors, it is hard. And second, our code seems like live, but there are many structures for live system, and each step like sending data or passing model, they all spend time and times are stacking. So our real time increasingly shows fast time motion, and also error is stacking. We are trying to make better structure until final proposal.
Right. Hi, my name is Shinza Ri, and who will explain the improvement progress and the plans. So first, we got new data sets by extracting from new points. It means new joints. So we extracted new data from left hip, right hip, left wrist, and forehead. The creation for choosing the above points is whether the IMU can be located in daily life. We thought about the smartphone in left hip and right hip, smartwatch on our wrist, and the AirPods on our head. We refer to official explanation in SMPL, and we can make new data sets. Now let's see the model structure. The original pipeline can be divided into 2 subtests, and the given figure shows one of them. It's estimating joint rotation to predict the user's pose. As you can see, there are 3 stages utilizing bidirectional RNN models. First, from the inertial measurements measured by IMUs, we estimate the leaf joint position. What I mean by leaf joint here is a joint where the IMU sensor is mounted, so we can get direct data for these leaf joints. Then, with estimated position of these leaf joints, we estimate again the positions of the other joints. Then finally, we regress the joint rotation theta from position of the all joints we have estimated. And all 3 given stages are done by using bidirectional RNN models to deal with natural ambiguity of pose estimation with few IMU sensors. To be specific, let me give you an example. So if the user is standing still or just sitting still, the data from IMUs for both situations would be almost identical. Then it's infeasible to estimate the pose by solely using the IMU data at the moment. This is why we use RNN models here. Now let's move on to the next subtask. It's about estimating global translation, or in other words, the velocity. As we do not have any direct distance measurements, we should rely on the IMU data alone. And this renders the task challenging. So we divided the subtask further into 2 parallel stages. First, we try to estimate the velocity of the user based on the sequential pose estimation, as well as the probability that the feet is on the ground. And the upper part of the figure demonstrates this process. Second, we try to regress the velocity directly from the joint positions and inertia measurements, as the below part of the figure shows. And after predicting the velocity by these 2 methods, we combine them to produce a single but more accurate velocity. We call it fusion process. Note that TransB1 uses bidirectional RNN model, while the other utilizes normal or unidirectional RNN model. Okay, let me introduce how each RNN model is constructed. It has 5 layers: an input layer, and a linear layer, followed by 2 LSTM layers and another linear layer. Currently, this can consider the context, but not enough. So we are trying to substitute the LSTM layers by the transformer decoder. It's well known that the transformer is suitable for this kind of tests. And this is the end of our presentation. Thank you for listening, and please feel free to give any comments, questions, or feedbacks. Thank you.